Hi, my name is Mark Jessell. I'm going to be presenting today on reproducible 3D model construction using map2loop. And I'm talking about building 3D geological models automatically from raw data using a series of Python algorithms that we've developed over the last couple of years in the scope of the MinEx CRC, the Loop 3D Consortium, and more recently as part of the Data Analytics for Resources and Environments project, DARE. You can see there's a long list of co-authors and even longer list of sponsors. My apologies to the government of South Australia, whose logo I'm hiding with my beautiful head. So what I'm going to be talking about is how to get from the left-hand side, which is raw geological data in the form of geological maps, and we can argue whether that's really raw or not. Of course it isn't, but it's it's data that's available across the continent and across most continents in the form of vector data, GIS layers, online geological servers, GIS servers, and the like. And what we need to be able to do is to automate the process as much as possible of going from this raw data to producing 3D models, because it removes the geological bias, which is so inherent in our modeling process as it stands today. So how do we do this? Well, we write a bunch of Python code, and what that Python code does is it takes information like this, and this is a geological map from the Hamersley Range in Western Australia. It's refolded folds with quite a lot of faulting going on as well, as you can see. We can extract the geological information from the geological polygons, from the fault polylines, from the outcrop points, from the DTM, the digital terrain model, and from the Australian Stratigraphic Units database, ASUD. And we can recombine this information to get all of the information we need to build a 3D geological model. So what does this look like? Well, we have all sorts of different types of information in these data layers. We have positional information, such as the location of a fault or the location of an outcrop measurement. We have gradient information, so the dip of bedding or faults. Topological information, so the relationship, spatial or temporal, between two geological features. Digital terrain models, and then really importantly, our conceptual information, which we can codify, which is essential to building 3D geological models, because we never have enough data to build unique models, even with all the data that we may have. So we always have to add our preconceived notions to this, but it's important that these are codified notions so that we can reproduce what we've done. These data and concepts are then combined in various different ways to produce augmented data sets we can then feed directly into 3D modeling packages. So what sort of data do we get out of this? This augmented data might look like the contacts between units, which at first sight might seem to be a simple task, but in fact what we have to do is we have to get the X and Y from the polygon layer, the Z from the digital terrain model. But then we also have to work out what is the basal contact of each stratigraphic unit, because 3D modeling packages don't want the top and the bottom of a stratigraphic unit. They want one or the other. So we have to use our topological analysis of the map to work out what the basal unit is, and that we can feed into the 3D modeling package. On the right-hand side, we have the faults, and here you can see we're ignoring some faults because we've got a decision that's made to model the longer faults, and that's the sort of thing that's easy to do when you have an automated process. We can also get the fold axial trace information from the maps, and on the right-hand side we can go a bit further, and each colored dot here is the estimated true unit thickness based on the apparent thickness that we can measure on the map itself from using the algorithms, and an estimate of the local dip of the bedding, which we can get by various interpolation techniques of the observed bedding information. And that allows us to combine those to get the estimated unit thickness. And that's really interesting because we can see variations along a unit in its unit thickness, which tells us perhaps something about the change in sedimentary conditions, sedimentation rates along locally variable, or it might be due to some later structural deformation. On the left-hand side here, we can see the fault offsets, which we're calculating in a similar manner to the true thicknesses. Here we can calculate the apparent offset from the offsets of stratigraphic units at the surface in the map. We can then combine that with estimates of fault dip, and usually we have to guess what the displacement vector orientation is, but we can get relative displacement variations along a fault, which allow us to understand which faults have got larger displacement on them, but how those displacements vary along the length of the fault. And that can be interesting for understanding variations in damage and therefore porosity and permeability. On the right-hand side, it's another measure of fault offset that we can use using a slightly different technique. We go to the next slide. We can also look at different types of relationships between different features in the geological data. So on the left, we have the stratigraphic relationships. Each rectangle is a stratigraphic unit, and the arrow points to the unit that's in contact with it, but older than it. And we can see that there's some more complex stratigraphic relationships than a simple layer cake that we can extract. And we can do this just for the area that we care about, i.e. just the area where we're going to make a 3D model, rather than taking the generic stratigraphic information which might apply to a whole map sheet or even a whole state. On the bottom right, we can do the same sort of analysis looking at fault-fault relationships, and we can extract out which faults are, and each of these rectangles is, the blue rectangles is a fault in this case, and we can extract out which faults are in contact with other faults, and therefore which faults are probably going to be the major faults in terms of controlling deformation in the region. And again, we could use this as a criteria for deciding which faults to model in our 3D modeling system. And then on the top right, we have this table where the columns are faults and the rows are stratigraphic units. And when the intersection is green, it means that that particular stratigraphic unit is intersected by the fault somewhere in the map. And again, that gives us information about timing relationships between stratigraphy, stratigraphic deposition, and deformation. We put all of this into our code, and 15 minutes later, out pops something like this. This is using the loop structural modeling engine. So it's a perfectly respectable 3D model of the area in question. You can see on the left-hand side, and we can compare that with the original map on the right-hand side, and you can see that there are variations due to the simplification of the 3D modeling process, but that's always going to be the case. We don't want to have, and we can't reproduce all of the fine detail in the map view in 3 dimensions. So we've got a very fast way of producing 3D models, but more importantly, we can actually start to extract information from the 3D model itself, of course. So here we're looking at wall rock displacement. We can see the legend on the right-hand side, showing us which are the grabens. So this red area, red striped area is the graben. We can see that there's some horse as well. We can see variations predicted from our 3D modeling. So what have we gained from this approach? We've got faster models. So once we've input the logic for a particular map set, we can produce a new model of any area within that map in a matter of minutes. It's reproducible. Every time we draw a rectangle around the same bit of the map, we're going to get the same model. It enforces unbiased separation of the primary observations, interpretations, derived data, and the conceptual priors that we needed to build our models. And finally, it provides homogeneous pathways to geophysical inversion, sensitivity analysis, uncertainty quantification, multiscale modeling, and value of information studies. So hopefully what you've seen here is the future of 3D modeling, but at the moment it's very much a proof of concept, so use it at your own risk. If I move my head to the other direction, you can see the link to where you can download the code from. On the other corner, you can see the website for the Loop 3D project, for which this is a part. And at the top, you've got my email. Thanks for your attention.